Hi, my name is Aleksandra, and I'm a software engineer at Google, working at Kubernetes Autoscaling team. And today I'll talk about how to add support to a cluster autoscaler to run it on your own cloud, on an environment not yet supported. So let's start with what is cluster autoscaler. It's an open source component, and I'm one of the maintainers of it. It runs as a pod in a cluster. It's there usually on the master node, and its responsibility is adding and deleting nodes to the cluster as needed by the workloads deployed there. And the code can be found on GitHub under Kubernetes/autoscaler. There are several autoscaling components there. It should be easy to find. So when we tell the story of cluster autoscaler, we usually talk about pods and nodes. We tell how it runs bin packing simulations to ensure that it adds the correct number of nodes or that the nodes can be safely removed. We focus on how it carefully drains the nodes one by one, but deletes the empty ones in bulk. But this is only half of the story. The other half is that nodes here are just Kubernetes objects. This is what you get if you run kubectl get nodes. But underneath, they correspond to VM instances, usually, unless you run KubeMark or virtual kubelet or something like this. So in practice, if we see an empty node and we decide to delete it, it's not enough to use Kubernetes API to try to delete node objects, right? Then it would result in a VM still hanging there, user still paying for the VM that can't run anything. So this is not good, and we don't do that. What we do instead is we want to delete the VM, and then when it gracefully shuts down, the node will disappear as well. So similarly, when there are pending pods and we want to add a node, we don't want to create a fake node object. What we want to do is to spin up another VM instance that will register as a node in the cluster, and then the pods can be scheduled there. So this may all seem fairly obvious, but it's important from cluster autoscaling point of view to divide the two. There is the cluster state we can observe and interact via Kubernetes API, and then there are VM instances that we can access only through Cloud's API. And well, the moment we use two APIs to get two data sets and we need to correlate one with the other, we start running into problems. So problem one is how do we match node to a VM instance? This one is easy, right? Node objects have provider ID, which should be set to some unique resource identifier that can be used to interact with the instance using Cloud Provider's API. That's how it works, in most cases at least. So the first thing you need to ensure when you want to run it on your own cloud is that the cloud controller for your cluster sets these provider IDs correctly, because cluster autoscaler absolutely depends on this. So we can match them, but what if there's a node with provider ID set and you can't find an instance with that provider ID? What if you have an instance that looks like it should belong to the cluster, but there is no node with matching provider ID? And it might be tempting to say, okay, this is not our problem, this is just some instance, it doesn't belong to the cluster. But what if it was cluster autoscaler, adding a node, created a VM instance, hoping it will register as node, join the cluster, run pods, but it didn't. If we just ignored it, it may never be cleaned up, it may be stuck, perhaps such instances can accumulate. So in addition to nodes having correct provider IDs, it's required for us to be able to list all instances that should belong to the cluster from Cloud Provider API. On to problem two. So how do we actually start a VM that will become a node? There are many ways to bootstrap a Kubernetes cluster, and in most environments, there is more than one way to create a node. You can use some sort of config management tool for deploying your cluster. You can use custom scripts for it. Cluster autoscaler doesn't know about any of that. So in order to spin up a new instance, it needs to know something, and this something we will get to. But the first assumption important here is that it makes an observation that if there is a node A and it corresponds to a VM instance B, then perhaps if we add another instance that looks just like B, it may register in the cluster and the node will have the same scheduling properties as the original node had. And by properties here, I mean anything that affects scheduling. All the resources, taints, labels, the availability zone. All of them are supposed to be identical. So this approach of using the existing nodes as blueprint helps us handle the case when there are different types of nodes in the cluster, right? It works out of the box. If we want to add a bigger node, we just request the same instance as that bigger node is running on. That's fine. But then, if we want to check all the nodes in the cluster, we will quickly run into scalability issues, right? There may be so many nodes in the cluster, and it doesn't make sense to run the simulations on all of them. So there's another observation, and that is that in most clusters, especially large clusters, nodes aren't individually much different. There are several types of nodes, and usually several dozens of nodes of every type. So if we just group them into some sort of sets, we call them node groups, because we like obvious names, then we can, for example, use just one node from each node group as blueprint for adding more nodes of that type. So this abstraction has an obvious benefit of optimizing the scale-up, which is one of the reasons we use it. But another benefit, perhaps kind of unexpected, is that by adding it, the core logic has a very convenient way of requesting more instances. Just like when you have a Kubernetes deployment or replica set controlling pods, you just provide a blueprint, and when you want more replicas, you increase the number of replicas set. So with respect to scale-up, node groups work pretty much like this. And it's very useful, but it's not a Kubernetes concept. There is no such thing as node group in a Kubernetes API. This is an extra layer of abstraction that is added in cluster autoscaler. And its purpose is not to be specific to any environment and to be as useful as possible. But it turns out it becomes very much cloud provider specific very soon, because the nodes are started differently in different environments, and for other reasons I'll get into in a second. So how does it look like? This big blob in the middle is cluster autoscaler binary. It, of course, contains the core algorithm, the logic that decides whether to add a node, what type of node to add, where to reschedule the pods, which nodes to delete. It imports schedulers code, which is important because this is the default scheduler from core Kubernetes, and it doesn't make a guess, will that pod be able to schedule on this node? It checks it running a simulation of the scheduler's code. So if you use any scheduler extenders or custom scheduling solution, it may not work very well with cluster autoscaler. And it observes the cluster state by using Kubernetes API, which is obviously the same in all environments, so it can be used directly. But in order to interact with the cloud API, it has also a cloud provider module, which is, of course, different for every cloud provider, but all of the logic of interacting with that cloud provider is encapsulated. So the main thing to do when running it on a new environment is to write a cloud provider module for that environment. How to do it? Well, there are very few requirements for how this cloud provider module will interact with cloud provider API. It's super specific to environment. Every cloud works a little bit different. And from cluster autoscaler's point of view, it doesn't really matter how it gets done as long as it gets done. There are only some minimal functional requirements that must be achieved in order to make it work. But cluster autoscaler logic depends on cloud provider module behaving in a very specific way. And this is what I'm going to focus on. So the entire surface is not very impressive. It's just two Golang interfaces connecting the main logic and the cloud provider module. And the first one is primarily responsible for providing node groups, so they can be really thought of as a single thing to implement. And just split into two for some syntactic sugar. So how do we implement these node groups? We don't have them in Kubernetes. We really need them in Cluster Autoscaler. Well, the good news is, and this is what actually all existing implementations do, that most cloud already supports some sort of VM groups. So you can just deploy your cluster in a way that all nodes will run on instances that are part of some instance groups, and all nodes within that group are identical, and then implement cloud provider module in a way that interacts with those groups, requesting new nodes based on some template, which is, like I said, specific to your cloud, and deleting some nodes. So, as usual is with good news, it's followed by bad news. These groups work slightly differently for every cloud provider, but they rarely work out of the box with Cluster Autoscaler. It's mostly related to how these groups tend to limit the user's ability to control their machines. So let's have a look at what is required to make the node groups abstraction work for us. There are two critical requirements of a node group. First is that all nodes within it must be identical. And I mean identical with respect to scheduling properties. All resources, the labels, the taints, the availability zone. This one is often overlooked, but if your workloads depend on it for scheduling, it must be the same for all nodes in the node group. If you want to have similar nodes across several different zones, just have several different node groups. That's fine, okay, it will work, it will save you a lot of trouble later. And the second requirement, no less important, is that we must be able to delete a specific node. Cluster Autoscaler corners, drains, and deletes nodes, and it wouldn't make any sense to simulate scale down if in the end we could just request, okay, remove 2 instances, I don't care which. We very much care which instances are going to be removed. So these requirements translate into some requirements for VM groups that must be fulfilled in order to make them work as node groups. And I put something slightly different here than in node groups, because I believe that it is possible to use regional node groups, for example, regional node groups that have nodes in different zones and artificially split them in cloud provider modules into several node groups, one per zone, if you must use regional VM groups, but you must be able to create instance in a specific node group and therefore in a specific zone. And the requirement to delete a specific node obviously translates directly into a requirement to delete a specific machine. If you can't do that, then that node group may not be, that VM group may not be very useful for you. So what if there is bad news? There is no VM groups in your cloud. Perhaps it's just starting out and decided not to implement it yet. Or perhaps the node groups are frankly unusable for this purpose. You can't delete a specific machine, or you can only create a regional node group which will always have the same number of nodes in each zone. So if you add 1 node, it will actually add 2 or 3, depending on the number of zones in spans. So in my opinion, not all hope is lost. I haven't done it, I haven't seen anyone do it, but I don't see any issue preventing implementing node groups directly in cloud provider module. I believe it should be possible, although of course it's going to be much more complicated because you will effectively have to implement the logic of VM instance groups inside this cloud provider module. But in principle, I believe it's possible. So this is enough for the basic functionality. To make Cluster Autoscaler add some nodes, delete some nodes, more or less work for your cloud. But there are some features that it may not be obvious why, but they are optional. So for example, the assumption that we always use existing nodes as blueprint for a group. It works very well, except when you really want to delete the last node of that group. For example, it is a GPU node and it's only useful when the batch job is running. Or for some other reason, you have expensive nodes that you really want to scale down to 0 instances in that group. Scaling to 0 is trivial. We can just delete the last node. The problem is, without a blueprint, we will not be able to scale up again. So what we can do is provide a blueprint. And we do it by implementing an optional method in node group interface, using which cloud provider module will return a fake node object, how a node in that group would look like if we requested it to the core algorithm. And then we can set the minimum size of this node group to be 0, and Cluster Autoscaler should be able to scale to and from 0. Scale from 0 might seem like pretty obvious, but sometimes it requires non-trivial logic to, for example, parse the instance template of a VM group or something like this. It really depends on how you go with the implementation. But it's very useful. And so the other option we might want to have is to have smarter selection of the node to add. Because for some cases, only one node group may be a suitable fit for the pods that are pending. But in other cases, for example, adding 2 nodes to one group or adding 1 node to another group will both allow some of the pods to run. We call such possibilities of expanding the cluster expansion options. And by default, if you do nothing past no flag, the random one will be chosen on scale up. And, well, this is obviously not optimal, because sometimes you might clearly prefer to run your pods on one 60-core machine than on 15 one-core machines. So there are other options to select from that should work out of the box. For example, most pods strategy, which basically selects the option which will allow most pods to schedule. Least waste option, which will calculate how much spare capacity will be left in the cluster, how much CPU and memory, and decide that expansion option that leaves the least unused space is the best one. This seems like really close to what we want to achieve, right? We want to avoid wasting resources. But as it turns out, the users really care about wasting one resource more than about any other. They want to avoid burning money. If a 16-core machine is cheaper than one 8-core machine and one 4-core machine, that's fine. They are happy with 16-core machine and burning the 4 cores. So this is super cloud provider specific, right? Pricing model is very different for every cloud provider, and it's hard to keep up with it, and it keeps changing, and there is not always a consistent API to get the prices of VMs. So how do we deal with it? Well, we introduced even more abstractions that are supposed to be cloud provider agnostic into our algorithm. You can use a pricing expander, which should calculate the best utilization in terms of cost efficiency if you provide us with a pricing model. And this pricing model needs to answer 2 questions. First is how much it costs to run a given node. This one is obvious, right? We want to know how expensive that option will be. So this is one thing, but there is another, perhaps less intuitive. How much it costs to run a given pod? And why is that? Well, in terms of cost, expansion options that, for example, allow you scheduling just one pod on one node, but this is a very small node, will always win, even if that pod would fit with the other pods on a big machine. So instead of adding a small machine for this single pod and then adding a larger machine for the other pods anyway, we need to calculate how well utilized this will be. We need to factor in how many pods are served by this expansion option, essentially. So this abstraction of how much it costs to run a pod is very much, it's not reality. It's not how much you will pay for this pod. It is based on the cost of raw resources like CPU and memory that this pod requests, so that if it was scheduled on a perfectly utilized, perfectly sized machine, it would cost at least this much. It is how much it must cost to run this pod on this cloud provider. And then using this and some math formula which was basically invented to make sure that the thing is behaving as we want it, we can select the expansion option that is the most cost efficient. And it should be independent on cloud provider. I hope it is. But if you have any questions or are interested in implementing it for your own cloud, please let us know. I'll be happy to find out if it scales as we thought. So a small note on dependencies. There are obviously multiple problems with cloud provider modules. It's hard to add support to a new cloud and hard to maintain it in main repo. There are cluster autoscaler releases, and if update to your cloud requires a release to be rolled out, then, well, you may have to wait for that release, and it puts an extra burden on maintainers, and all of this has to be reviewed by people who will never run your code and stuff like that. So this is the same thing that Kubernetes, cloud provider code in Kubernetes faced, and it has been resolved by moving, or is being resolved by moving to out of 3 cloud providers. The other problem is that you are likely to be implementing the same thing, or slightly different but more or less the same thing, over again in different places. Perhaps you have some automated way of creating clusters and bootstrapping Node, and then you will be duplicating that logic in cloud provider, their module, or reverse engineering it. And third, and this is like the nightmare from maintainers' point of view, is the growing number of dependencies. We simply don't have the manpower to audit all of them, and we really hate increasing this binary size even more. So about these dependencies, there's a fun fact. This is how some Go apps look like. They have some actual logic. They use some dependency management tool, GoDeps or something newer and fancier, and these dependencies are sometimes stored in vendor directory. So this is how core Kubernetes looks like. It has the components, which are often vendored, and they are separate from the main repo in order to not have to vendor the whole thing. So they are separate repo, it's fine. We can just use them, right? Except they are actually developed in core Kubernetes under the staging directory, which means they are synced there, but the core Kubernetes itself symlinks in its vendor to staging so that the compatibility is maintained. So this works for Kubernetes with the assumption and recommendation that core Kubernetes is not intended to be vendored. Guess what? Scheduler code lives in core Kubernetes, and this little component called cluster autoscaler depends on that. So we must somehow deal with it. And the way we do it is that we do some hacks around our dependencies to use the core Kubernetes dependencies instead of checkout as a fixed version. And then any dependencies that we can't take from Kubernetes because it doesn't have them, we put in an override. So there's a bit of nasty hack here, but it also, I hope, explains why is it so complex for us and difficult to maintain the growing number of dependencies, and why we want to avoid them as much as possible. So on to a better, brighter future. Cluster API. The idea behind this thing is very interesting. Like in Kubernetes, you have deployments and replica set managing pods. What if you could have machine deployments and machine set managing machines, the VM instances, an abstraction that is Kubernetes-like and independent of cloud provider? So if you want to create a node on any cloud, you just call cluster API and set one more node on that cloud, please. Please create a node group like this in this cloud. So this is very similar in some way to the node group abstractions we already used, although it has it takes it much further, obviously, allowing rolling upgrades and stuff like this. And it also means that you will implement this for each specific environment only once. If you implement Cluster API for your cloud, then any component that wants to manipulate your cluster, the resources, the machines, can just use it and doesn't need to have the specific code. So maintaining that code becomes much easier because it's contained in one place. And also, if you have clusters deployed on different clouds, you can manage them using a single API with many implementations, each for a different cloud. So you can find out more about it on SIG Cluster API. And this is just one possible future. I don't know if it's going to happen, but if it does, I think it will help us a lot with managing dependencies and stuff. Instead of having cloud provider modules in Cluster Autoscaler, we will have a sort of adapter module that basically implements our abstractions using the Cluster API. And then it calls the Cluster API for each given cloud to request VMs, delete VMs, discover VMs, read instance templates, and create a node info out of it. So that way we can have all the features without any cloud provider specific code in our binary, and it will basically work out of the box. So the obvious question, to me at least, is if we have this, why talk at all about implementing cloud provider modules anymore? Why should we add another one when we should be migrating to this? The answer is reality. Cluster API is not yet ready. And by this I don't mean that it's not yet implemented everywhere, but also that the API itself is missing a critical requirement for Cluster Autoscaler. It's missing the ability to delete a specific machine. And if we can't do that in a transaction, reduce the size of machine deployment and delete a specific machine, then we can't migrate to it. So this is like the major blocker right now. But there is ongoing work to make this migration possible, perhaps step by step, perhaps for some cloud provider first. And I believe this will be a great thing if it happens. So that would be it. If you have any questions, I believe we have a few more minutes still. Feel free to ask about anything, and if you would like to find out more or run into any problem or would like to ask Cluster Autoscaler maintainers about anything, you can always find us on GitHub, open an issue in that repo, or ping us directly, or on Slack, SIG Autoscaling. Thank you. Questions? Let's wait for the microphone.
In Cluster Autoscaler, we can configure different node group. But if we migrate to Cluster API, is there any alternative ways to do the same things?
So the question, if I hear correctly, is that in Cluster Autoscaler we can configure settings for each node group, and with Cluster API will that be possible? I believe so, because Cluster API will provide us with abstraction like machine deployment and machine set. And if your cluster is deployed using these abstractions, then from the user point of view, it should work more or less the same.
Okay, thank you.
Just a quick question. So far, I can see you are, I really like this project. But for the node itself, in the future, for example, if I have a different CNI, or all these kind of things, because so far we are not only talking about the node itself, right? Also the storage, also the network. So will that all be included in this Autoscaler API, Cluster API? Will that also, all the effort will be put in this project? If we are dealing with different kind of CNI interface. For example, like on-premise, I can use Weave, or I can use some other SDN solution. Can I pick from this, or this project only generate nodes?
So I believe this question about cluster API, how it will deal with storage and different CNI drivers and stuff like this. So the answer to it is I honestly am not sure about it because I'm not working on cluster API directly. But from cluster autoscaling perspective, I believe it should be pretty independent of that.
Okay.
Basically, if nodes in some machine deployment have storage, then we will assume that other nodes deployed there will have storage. I am unfortunately not able to answer your question about cluster API plans for support of this.
Okay, no problem. Thank you.
Okay, so maybe you can pass the microphone.
Yeah, thanks. I can help a little bit because I work on the cluster API. So yeah, CNI, different kind of CNI support is in the discussion of the cluster API, but it's abstraction and Autoscaler should not care about it. Yeah.
Thank you.
But I do have the question. So, how you work with the cluster API? We have the cluster API. Weekly meeting and discussions, and the two projects going to merge or?
Right, so the question is how do we work with cluster API and are those projects going to merge or something? And the answer is, I believe, no, because we are doing different things. We as Cluster Autoscaler would like to use cluster API, but we don't actively work on cluster API. Like I don't, of course. That's only speaking for myself. Other people obviously do. And yeah, I don't believe these projects are going to merge because they are essentially doing different things.
Thank you.
Okay. So thank you very much again.